In this video, we're going to discuss how you improve those estimates that we did in section 5.1. So how do you improve your left and right hand estimates, and actually how do you find the exact area that's underneath a curve? So recall last time we had this table where we were looking at the speed that the car was traveling over a time from 0 to 10 seconds. And so in this graph, the darker colored purple, that represents our left-hand endpoints. So these are our left-hand endpoints. And you notice those purple circle or those purple rectangles are underneath the curve. And then the lighter ones, we would be using these endpoints in blue, and those were above the curve. And that was called our right-hand sum. And so what we want to try and do is figure out how could we find this exact area underneath the curve. Okay, so here was this first one is our previous example. And we would say n equals 5. In other words, we use 5 subdivisions. Or delta t would be 2. Our intervals were 2 seconds long. If you created more subdivisions, like in this example, underneath the same curve, let's say we did, in this example, there are actually 10 subdivisions. What you're noticing is now all of a sudden it's starting to fit the curve much, much better. And here, if you divided 10 subdivisions of 10 seconds, you would have delta t equals 1. In this example here, this is actually 40 total subdivisions. If you divided 10 seconds up into 40 subdivisions, delta t would be 0.25. And so what we want to do is continue to add subdivisions until we reach this last example. This would actually be n equals infinity. We have created as many subdivisions as we possibly could. If we could make an infinite number of subdivisions, we would have the exact area under the curve. And delta t would be what we call infinitely small or almost 0. So if you could create an infinite number of subdivisions, the result would be the exact area underneath the curve. In section 5.3, we're going to actually talk about a method or a theorem that allows us to find that exact area. But first, let's define how we mathematically represent the exact area underneath a curve. The exact area underneath the curve is what we call the definite integral. So the exact area under the curve of f of x from x equals a to x equals b is defined by this thing here. We say this is the definite integral from a to b of f of x dx. So counting the area above the x-axis positively, so the area above the x-axis is positively, and the area below the x-axis negatively. So what we're saying is the exact area underneath a curve is the same thing as this notation. That notation is saying the area underneath f of x from a to b. So this is really just a notation thing. So let's look at applying that notation. So here we have a graph of f of x. We count the area above the curve positively and the area below the curve negatively. So this is telling me, for example A, to compute the area underneath f of x from 0 to 3. A equals 0 and b equals 3. So from 0 to 3, I have 5, 6 below the curve. We count that negatively. So negative 5, 6. And then we count the area above the curve positively. The area above the curve is 16 over 3. If we were to compute that, I would say that's negative 5 over 6 plus 32 over 6 is really 27 over 6. And we can simplify that to 9 over 2. So we're saying the area from 0 to 3 of f of x dx is 9 over 2. This is asking me only for the area from 0 to 1. The area from 0 to 1, or in other words, this space here, is all below the curve, so I'm going to call that negative 5 over 6. And this last one, this is saying the area under the curve from 0 to 3 of the absolute value. So using absolute value, 5 over 6 would actually be now positive. Plus the absolute value of 16 over 3 is 16 over 3. So really we're doing 5 over 6 plus 32 over 6 is 37 over 6. So that's the exact area underneath the curve. Let's say we want to use a table to estimate the area underneath the curve. Well, recall that our left-hand sums and our right-hand sums gave us pretty good estimates, and what we can determine is that the value is actually somewhere in between those two. So if we want to estimate the area, what we're going to do is use a combination of the left-hand sum and the right-hand sum. So let's first do a left-hand sum. If I look, each one of these subdivisions is 3y. So using the left-hand sum from 0 to 3, we would be doing 3 times 32. From 3 to 6, we have a space still of 3. 3 times 22. From 6 to 9, 3 times the left-hand number is 15. And from 9 to 12 would be 3 times 11. So we have 96 plus 66 plus 45 plus 33 equals 240. And that's actually an overestimate. And the reason I know it's an overestimate is because these numbers are decreasing. So let's try and compute the right-hand sum. Now from 0 to 3, for 3, I'm going to estimate the right-hand number is 22. From 3 to 6, so for 3 times the right-hand number would be 15. From 6 to 9, so for a distance of 3, using the right-hand number, 11. And then from 9 to 12, 3 times the right-hand number is 9. So I've got 66 plus 45 plus 33 plus 12 equals 156. Now what I know is the actual value has to be somewhere between these two. So I'm going to guess it's just the middle of them. So I'm going to guess from 0 to 12 of f of x dx is somewhere between 240 and 156. So I'm going to guess it's the middle of those. So 240 plus 156 divided by 2 gives me a middle number of 198. So I'm guessing the area underneath that curve is 198. Let's look at how we could do that graphically. What I would do here graphically, and I want to do the area from 4 to 16. Okay, so I know my A value is 4, my B value is 16. And if I look at my subdivisions here, they're 4 wide, so I'm going to say, okay, my delta x is 4 wide. And my number of subdivisions is I've got 1, 2, 3 subdivisions, so I'm going to use 3 subdivisions. And essentially what I'm trying to do first is I'm trying to guess, okay, what is this area here? What is this area here? Well, I know its width is 4. Now, on the high end, well, actually, let's do the low end. The low end, I've got a value of 2. On the high end, I've got a value of not quite 3. So we know we want to be somewhere between 2 and 3. I'm going to guess maybe about 2.5. Then we need to do this next area. We're going to estimate this area in here. Again, we've got a width of 4. Now the height of that's somewhere between 3 and 3.5, so I'm going to guess about 3.25. And then we need to guess this area here. Again, the width of that is about 4. And now I'm looking at something between 3.5 and 4. So I'm going to guess about 3.75. So if we multiply those out, we get 10 plus 13 plus 15. I'm going to guess that that area is about 23 plus 15. That total area underneath that curve is about 38. Now when you get done with this video, we don't quite have a way to do more complicated functions. So like, how do we find something like this? Well, in section 5.3, we're going to learn a specific way to do that by hand. How do we find these areas by hand? But for now, you can do these with the TI. And what you'll notice is there is a video directly below this one explaining how to find these on your graphing calculator. So please make sure you watch that video. If you can't understand that video, you're welcome to email me, and I will walk you through how to use your TI. We can set up a video conference, but I think that video below will give you pretty good direction. What I want you to do is, after you watch that video below, try this one on your graphing calculator. And what I'd say you want to be careful to do is make sure you put this x squared in parentheses. And so give this a shot, and the way it should look on your graphing calculators, it'll actually end up looking like this. But plug it in, make sure you get the value 2.176489794. Something, you should get that value from your graphing calculator. If you're having a difficult time figuring out how to come up with that value, please email me and I'll be happy to walk you through that. But otherwise, check out the video below and it should get you there.